Okay, yeah, I think everything should right now work, which I thought until yesterday would be effortless, because last week we already had some practice round, right? I mean, and it worked quite well. Okay, the YouTube, I mean, perhaps the first 5 minutes should have been recorded as well. Let me reduce the volume of the microphone a little bit. Is this okay? Is this better? Or is it now all of a sudden, now it's gone? Yes. Okay, is this, okay, now I can hear a bit of reverb. Is it good or should it be louder? Louder, okay, I will push it to the max. I mean, not, so I have one more notch. I mean, the people in the back, louder? No? Okay, good, yeah, they shake their head vigorously, so let's not, let's not go there. I also get the impression if I stand here, it's more echoey than there. Perhaps that's just my impression. So last week I had a bit of a ghetto setup where I stole a USB audio input and then plugged it into my laptop web, and not using the official Teams room that we have here, and that was allowed. But yesterday, university decided, like, no, we now have a new system which is going to work much better. Okay, well that took me better half of an hour. Okay, I know on YouTube that's strange. On YouTube you should hear me, Isabel, because if people can hear me on Zoom. And given that this hall is used pretty much continuously, it's not like in the middle of the day, like, let's try out some new technical first week, second week of the semester. I mean, we have other things to do. So I apologize on behalf of the entire computer science department for the amateurism that we display, right? This is not us. It's a careful interplay between different parties. So, okay, I'm going to try to keep an eye out if the audio is now on YouTube. Otherwise, well, at least you have the slides that are being progressed very steadily. Good. Let's get started. Okay, that is something that somebody else will figure out. Good. Okay, lecture 2. Last week, we introduced ourselves a little bit into the topic of machine learning. What can we do, or particularly what are we going to cover in this course? Such that, well, at the end you can say, okay, I at least know the elements of machine learning. Today we're going to be diving into the first real topic, namely linear regression. You already know from last week roughly what it is, so we can dive straight in. And speaking of straight, that's the whole point of linear regression. Here we have, for our favorite running example, spending on advertising, and then, okay, how much product sales do we actually get out of it, right? We have investments in TV, radio, and newspaper, in thousands of dollars, and then we see, okay, what is the sales that we get out of it? Now, out of this, over many months and over many different locations, the data that we got, we want to see, okay, what is now the relationship between the two? What is the best investment? What is the best, the most bang for our buck, so to speak? Now, a straight line, as we already established last week, may or may not fit this data perfectly well, but that is something we're going to happily ignore away until a bit later into the course, right? Straight lines is what we have right now, and we're going to wield them with all that we have. So if we're now looking for these linear relationships, what questions can we ask? Why is this useful? I mean, what beyond the, well, it's fun to fit a blue line over true orange points. Of course, you can in general ask yourself, is there a relationship between, in this case, advertising budget, the X, and the target attribute, the Y, here the sales? Of course, if the evidence may be there, it's very weak, it may not be the best investment to make, but if the relationship is very strong, okay, well then go for it, right? Sales is not really my favorite running example, just as the book does. Personally, I like the more biological health applications much better, right? I mean, that's how large should the vaccine doses be for it to be properly effective, and well, how large should it not be to be too effective, right? I mean, disease dead, but patient too. I mean, that you want to avoid. Okay. Now, is there a relationship is one question, but how strong is it? That we can also tease out of a linear model, and much easier than with a more advanced model. But, a sub question is then, okay, how well can sales be predicted? So if this relationship is really strong, then I can predict quite well what is going to happen if you invest more, right? If the relationship is very weak, even if there's an upward trend, yeah, well, anything may happen. This particular case, which media contribute to sales? So we have TV, newspaper, and radio. That's the third one. Yeah, maybe there's an interplay between them. Maybe we only need one or two. Maybe we just invest in TV, the rest just sort of we get for free. Maybe it's actually really good to invest in two of them, and the third one we can let go, or maybe all three are important. Well, in this particular toy example that we had on the previous slide, it doesn't really matter so much, right? Nobody of us cares about newspapers. But if you do care about healthcare situations like I do, then, well, which combination of, let's say, drugs is the most effective, right? And you don't want to just, open the cabinet and, okay, pills for you, for everybody, right? And just see what happens. You rather give, let's say, very small doses that are very effective. How accurately can we estimate the effect? Now, I have to be really careful in my phrasing, because if I say effect, you should kind of already hear, what is the cause? But the problem is, in machine learning, unless you treat it really carefully, you cannot say anything conclusive about what is the cause and what is the effect. You should always talk about what are the dependencies, what are the interactions. Unless your data was really carefully collected, that you really know, well, these were the only things that were changed, and then we observed that and that. Okay, sure, right? Then you can start to speak a little bit about cause and effect. Otherwise, we need to be really careful. So many of you, we did a raise of hands last week. You took Statistics Lab. It's one of the courses that we invented to ensure that you in the third semester can already take EML and get started on the whole machine learning, AI, data science train really early on. I'm really happy with this course. Last year, I could already see a huge difference between those people who did take it and those people who hadn't taken it yet, because, well, they were later in their studies, in the study program, never had the chance to take it, and there was really a big difference. There's one thing I do not like about Statistics Lab, and it's essentially by design, which I helped out a bit with. There is no causality there. We really treat statistics pretty, well, let's say, old-fashioned, I could now say, and we really look at, okay, what are the basic notions, which is good for the third semester course. But again, the moment that you now have in mind, I want to figure out cause and effect, right? These drugs really cause this type of effect, these by-effects, or they kill a disease. Be careful, be really careful, right? Similarly with these investments, there can be tons of confounding effects, right? Maybe you're just throwing money out of the window and it's actually, there's some other channel that creates demand, right? For example, if you're advertising for ice cream, you can invest a shit ton of money during the winter, but probably sales are not going to react so much, right? And in the summertime, you can invest a lot, but even without doing so and just having your product on sale, probably sales will rise tremendously compared to winter, right? So you can save some money there. If you don't take this into account, yeah, well, bad shit can happen. Good. So hence, effect. How can we estimate it? Be careful, be careful. Can we accurately predict future sales? Now, that is something where, on the one hand, so prediction is very difficult, especially if it's about the future. Apparently, Niels Bohr said so, or somebody else who was smart. That seems like a very impossible thing to do, especially if I just said, okay, well, cause and effect, forget about it. But actually, prediction is comparatively much easier. This is something that we will treat in this course quite in detail. If there is a relationship between two or more variates, and it's strong, so we can predict, we sort of really see an effect in many, many different cases, that is great. But then we can still ask the question, and it's different from the ones above, is this relationship in fact truly linear? Are we using the right tool? Are we modeling the effect the right way? Ooh, I said effect again. And this is already going towards the second half or the end of today's lecture. We started a bit later thanks to the technical contraption here. So let's see how far we get exactly. Is there synergy? I already highlighted, hey, well, if we would invest in, let's say, just newspaper or newspaper and radio or any of the other possible combinations, we might get a boost in sales because they just reinforce one another. You first hear about the product on the radio, and then you see it on TV, and then you really have this craving desire to buy it. Might be. Maybe just one of these channels is enough. How can we tease this out of data? Well, that is something we leave for later. Let's start really simply with simple linear regression. In any type of data analysis, any type of machine learning, we always need to make some assumptions about the data. Where did it come from? What form or shape do we think that it takes, the relationship behind it? And in linear regression, we assume the following, which is ridiculous, but let's see, does this work? No, that doesn't work. So, okay, then I really need to do it like this. So, we assume that our data, our target attribute y, approximately follows, right? We allow a little bit of slack, this relationship. So there is an intercept, beta 0, this coefficient, plus then beta 1 times x. X is one of the predictors, one of the variables, right? And that's what we're considering, right? All the others we completely ignore. It's a tad simplistic, but hey, something's got to give. Such that we can say we regress, in this case, the sales onto x. So the sales we regress onto newspaper spending and so on and so forth. They're very simple, you could say ultimately naive, univariate model. You could say, okay, well, wait a second. I see two variates, right? I see y and x, yes, but we want to predict y, which is univariate, using x, which is also univariate. So, univariate. We have two coefficients or parameters. I'll be using both terms interchangeably. Beta naught, beta 0, and beta 1. So the intercept and the slope of the line that we're going to draw, right? Now, the moment that we have either, God-given or somehow we guesstimated the values of beta naught, beta 1, we obtain this one over here. We have the estimates of the coefficients. We have one particular x comes in, right? For one particular, let's say, village where we invested in the local newspaper or something like this. What are the expected sales there? That's how we get it out. So how do we now get our hands on these betas? And now they're wearing a hat, right? I'm using this the moment I estimated them, standard notation. We're given a bunch of training data where we have both the values for x, which are typically easy to obtain, and the values of y, which are often much harder to obtain. And typically we can only have about, history, right? And we want to use this model, the super simplistic model, in the future, where we do know how much we did invest, but not yet how many sales we made, or we are considering changing the amount of investments and then want to see what's going to happen. So our goal right now, in order to make this possible, is to estimate these unknown coefficients such that they fit really well in the future. Okay, how are we going to do that? We were out of coffee beans this afternoon. It's really bad. If you want to lecture, right, you need a bit of caffeine. So thanks, Club Mate. So estimating coefficients. We could, of course, just try and see what works best. And last week we already discussed a little bit, okay, how long were the black lines from the blue line or whatever color it had? Okay, we need to formalize this a little bit. We're going to formalize this using what is called a loss function. Right, so we have some model with some parameters, which we somehow guesstimated. And then we want to see, okay, well, how good or how bad is this model? Well, how much do we lose compared to having the perfect predictor? The perfect predictor is just the data itself, right? Which we know, given that, let me go back one slide, at the top left, we have this squiggly. Y is approximately beta 0 plus beta 1 x. What is the squiggly? We allow for a bit of noise in the process, right? There's very few processes of interest that have no noise whatsoever. So this is where we know that there is not going to be like a perfect predictor, right? There is some irreducible loss, just reiterating the term from last week. So what we now have is that we now have our predicted value y for point I, your coefficients, and this is the input, xi, then there is going to be some difference between our predicted yi and the true value yi, right? That's the error that we make. We want to make this as little as possible without overdoing it. This error we call the residual for this particular data point. And if we now simply would sum up all these residuals, we have the sum of residuals, and sums are fantastic, but sometimes we overpredict, sometimes we underpredict. And of course, if we underpredict, then, if we overpredict many times, but we underpredict as many times, we could still have a zero sum of residuals, which is kind of useless. So we kind of want to avoid that. And hence, we typically look, as loss function in regression tasks, at the residual sum of squares. Right? So for every predicted value and the real value, we just take the square and we sum over every one of them. Still nice because, well, 0 is best, that is optimum, right? It particularly penalizes these long black lines, right? If our prediction is really off, we have a square of it, right? So that makes it pretty bad. And if it's nice and small, okay, that's good, right? We allow for a bit of noise in the system. Note that by definition, this is a quadratic function, right? There's squares everywhere, but if you write it out. So here we just simply have the sum of the residuals, and if you write it out, okay, look, I mean, there's lots of squares and lots of, so beta and beta naught, beta 1 squared. This allows us to simply look at the derivative, set it to 0, and then we can find estimates of beta naught, beta 1 that are particularly helpful in driving this function down. So let's first start with some really basics. Y bar and X bar are the average values, right? I just sum up all of them and I just divide them by n. I will need this to achieve the following. So by doing this derivative thing, setting it to 0, this is what I obtain. For beta naught, what is my estimate? That is simply the average value of y minus the average value of x times beta 1. Okay, where does this come from? Well, let's first look at beta 1. There we have it. This is simply, I would like to zoom in a little bit actually, now that I think of it. We have at the denominator, we have the distance between the average of x and the actual value of x, right? How's that? Times how far does the current y value deviate from the average? That's the denominator. We sum over all these distances. This is again like a squared term. The denominator is simply just what is the variation that we have in x, right? So the moment that our predictions are perfect, everything goes to 0, everything is fine, and hence, well, then beta naught would be simply, I hear there's somebody or something making a noise here. Let me just check. Okay, no, it's a bit of, it sounded a bit like a small kid, so I just wanted to make sure that there's no small kids being harmed during the lecture. Okay, so if beta 1, if we get this part perfect, this here, this disappears, this vanishes, and then beta naught is just the average value of y, which is exactly what you would expect, right? If you just in one moment, just in one, I mean, mathematical moment, in one value have to say, give the most information about the data at hand, it's the mean. For beta naught, so that's y bar, that's the average, right? So the beta 1 is then, what can we explain in addition? And that's that. So beta 1, however, has all terms that we know. We have x bar, which we can compute from the data. We have y bar, which you can compute from the data. All these distances we can compute from the data. So beta 1, we can compute in one go. And then we can simply plug it in to the estimator of beta naught. And there we are. Simple derivation, do it on paper. You will find out that it's very natural. So what is one other aspect of this thing being quadratic? It means that it has a very nice shape, not just visually pleasing, as we see here, but the moment that we're a bit off, so this plot here, this contour plot, oops, so between beta 1 and beta 0 over here. So we have these concentric rings where they go up and up and up. So on the right-hand side, we have it, the residual sum of squares here in the z-axis. And here we have, again, this. There is a very clear minimum. It's unique. That's the best estimate of beta naught, beta 1. And the good thing is, and this is analytically very convenient, the moment that we're, the further off we are, the stronger, you could say, the learning signal is, like, okay, get the hell out of here. We need to adjust the parameters such that we get to this minimum, right? So it's both didactically very good and a bit stupid to show this already, because in the linear case, we can compute this minimum in one go. We don't need to look at these contour plots. But in incredibly many other learning algorithms, learning setups, you do not have this luxury, and you still want to have, well, the best, maybe globally, maybe locally, possible solution you can attain. And you can already see that from the right hand on the bottom of the plot, if you find yourself somewhere on this landscape, just by walking down until you can't go down anymore, you will find a good solution. That is the intuition, it's gradient descent. That is at the backbone of 90 out of 100 machine learning methods. And the other 10 are a bit weird. You also have stochastic gradient descent. Those of you already know a little bit about neural networks, may have heard of that. What do you do essentially in stochastic gradient descent? It's a bit hidden, but you kind of want to go to the minimum. And you take a step in this direction, but it's a bit like you had a little bit too much to drink, right? I mean, it's not that you're completely drunk and walk uphill, right? That you don't do typically, but it's sometimes like, whoops, and you take a random step. And that way, right, so if the landscape is not as smooth as it is here, that allows you to escape from what we call local minima, right? If there's multiple dips in this landscape, we sometimes take a weird step to the side, and then we go minimum again. That is essentially now. Now you know how 90%, maybe 100% of learning algorithms work. Good. Let's put this to practice. For this particular data, so we have the TV ads and then the sales. We plug in the formula I showed you in the previous slide, and we now get the following coefficients. Beta naught, so the average sales flat. The intercept is 7, and then we have a slope of 0.047. Okay, nice. So not bad, right? So for every 1,000 that we invest in TV sales, we can expect 1,000 times 0.047 extra sales, right? So, okay, if that is now useful or not, I mean, that is up for the marketing, the people of marketing. These estimates, both beta naught and beta 1, they're based on these orange dots, which I painstakingly copied from the book by scanning it and then placing them by hand. So it might not be exact, right? But this is essentially all the data we have, even without the extra jitter that I might have added to it. So we do get this value, beta 1 and beta naught. Can we trust them? If I would have given you on the same x-axis from 0 to 300, you can tell, by the way, that I wonder actually if this is me or if the book is just weird. Why on earth would there be less than 0 investments? I mean, did we get them for free? Were we paid to advertise our product? No, let's ignore this. I mean, sometimes during lecture you see these things and perhaps you should just shut up, but this was just too weird not to mention. If I would have given you double the amount of points, we would have been perhaps double the amount of certain that this line is the right line, right? I mean, if it follows the same trend. If it would have followed the opposite trend, then we would have been double so certain this is not the right line, right? If we would have taken away half the points, we would have been half as certain. What? Yeah, half and double are a bit vague, right? And that's how certain are we? I mean, can we trust this 7? Can we trust this 0.0475? Right? What are the accuracy of the coefficient estimates? And can we say, are they really significant? Is this 0.0475, is this a number that we should be happy about? Should we really go to the marketing, the boys and girls of marketing and show, look, really, it's amazing? Or like, okay, we should just stay mum and okay, you know what, give us more data. Now, before we can go there, we need to realize that we just found one line on the previous slide, right? And we said it's the best one. But there's, of course, many, many possible lines. However, at the same time, there's also only one line that is the true line. That's this one, that's the red line, right? The one that you would not cross. Then the red line is what we call the population regression line. So if we would have all data in the world, right? Then we would draw this line. This is the line of the true system. Well, we never have it, right? But it doesn't really matter. We can still pretend as if we have access to it, right? Maybe if we pray to the gods of linear regression, maybe we wake up and we get some divine inspiration. Now, the population regression line, as we already had established last week, will also suffer from this irreducible error, right? There is this noise in the system. So that means that the formula we had previously on the slide, where I had that y, our estimate of y or whatever, was a squiggly of beta naught, blah. Now it's an equals, because look, I have here my epsilon. Epsilon is now noise, right? So, and we can make some assumptions about the shape of this noise. I'm already go ahead a little bit, and our assumption is going to be that it has a 0 mean. So it's really centered around the line defined by beta naught, a true beta naught and a true beta 1, right? And we assume it to be of Gaussian shape in this particular case. There's exceptions possible, but right, 0 mean Gaussian shape. That's what the assumption we're going to make. Okay, good. Now, the let me actually just go to the next slide. So rather than having really all possible data, in practice we have just a number of dots, right? I mean, again, painstakingly placed. And from these dots, we can now do the whole, estimate beta naught, beta 1 dance, right? Like we saw on the previous slide. And we might get this one, the blue one, right? Let me play the thought experiment with you. Let's take out one or a few of these dots, of these circles. Well, obviously, or actually perhaps not obviously to all, I don't know, I do hope so, this line will change a bit, right? But already going ahead to, I think, next week, you can already you can already start to think about which dots would affect the line most. Which dots would be, well, the worst to take away, which dots would be the worst to place in addition, right? To get us either closest or furthest away from the population line. Sort of adversarial thinking. But okay, but let's just take a few out. We get a slightly different blue line, and so on and so forth. So now let's remove the dots. They're just very distracting. Essentially, this means that as long as we follow roughly the same distribution, the true mechanism, so the true beta naught, true beta 1, and whatever the error distribution is, and we just get a lot of different data sets, we fit a blue line. Essentially what we get is what we have here. So I have still the one population line that, unless I give you infinite data, you will never be able to really touch, unless you get really lucky. And all the light blue lines, I hope you can see them from the back. It's a bit light on purpose. These are all alternative lines that we could have gotten from the data just as well, right? This line, so the opposite diagonal, in theory, we could also have gotten, but that would have been a very adversarial sample of the data, right? We really would have needed to remove all the right points or the wrong points, depending how you look at it. Then we could have really screwed up that badly. Now, let's not think about that. So we have a process that we can ask, give me the same number of data points, and we can do this time and time again. And for each of those, we're going to fit a blue line. That gives us essentially a distribution of values for respectively beta 1 and beta naught, right? So rather than just 1 point sample for the data that we have, right, but this is the realistic case, we can sort of pretend that we can do this many times, and we get a nice distribution of these values. And by the assumption that we made that, hey, the noise, zero mean, Gaussian distributed, we can actually now start to say something about how likely the estimates that we got for our blue line, how likely they are from the red line's perspective. How far away are we? That's the intuition. So how do we do this? Let's take a first important step. I mean, what we want to know in the end is, are our estimates, are they biased or unbiased? And building on last week, right? I mean, the moment that in our model class, in our possible answers, the right answer is there, we just need to find it, right? Then we have the chance of having an unbiased estimator. If the right answer is simply not there, then we're kind of screwed, right? No matter which answer we give, we're always going to be wrong, no matter how much data we're going to get, right? Okay, now, one unbiased estimator that you already know is the average, right? If I just give you a bunch of numbers, right? And that's like in this case for Y, what are the sales? And I ask you to compute the average over this sample, that is an unbiased estimate of the population average. Because the moment I would give you more and more data, I mean, you would actually get close to the actual average, right? There's nothing, let's say, against you, or the deck is not stacked against you. Now, in that similar sense, if the data is indeed generated by a linear mechanism, then the least square fit, so the way that we find our estimates, right, and that is also unbiased. Just as much as just summing everything up, defining by how many numbers you have, is an unbiased estimate of your average. Now, the Gauss-Markov theorem, after a long debate, we decided to not include it explicitly, this proof, in the homeworks, in the assignments. Let's say I did not win the debate. I think this is the most important thing of this entire course. And I will say this a number of times, and I really do stress you to look this up, to read it up, to digest it, to eat it, whatever, right? I mean, that's really understand the Gauss-Markov theorem. But in a nutshell, what does it say? That the least square fit is an unbiased estimate for the population regression line. So if there is truly this linear line, then by least squares we will find it. And we're not going to be, well, there's nobody pushing us to the wrong direction. But, this is the cornerstone of statistical learning. We had a few other things that we wanted you to prove, and we did not want you to be completely overloaded with proofs, and hence the debate. And like I said, I lost the debate willingly. I'm not sure if you now won, right? That depends a little bit on how you see it. Perhaps we throw it into a next assignment sheet, who knows? Oops, I thought that I had a very nice introduction to the very first green plus, right? I used the green plus in my slides to indicate that what you're seeing on the slide, it's not optional, right? Absolutely not. I mean, if you don't know the Gauss-Markov theorem at the exam, I mean, I'm sorry, but then thou shall not pass. Depending on whether I win, setting up the exam, of course, right? And you can still have hope. No. The green plus is that there is way more knowledge available in the ESL book on this topic than in the ISLR book, right? So the green plus slides are the ones where you really want to look at the ESL book. The ISLR book will paraphrase like, yeah, this is kind of important. It's kind of a bit more important than just that. That's what the green pluses stand for. And now my introduction in the later slides to the green pluses is completely moot. Okay, now so let's go further. We want to know in the end, right, where we're going, how accurate is our estimate of a beta naught, respectively a beta 1. That's what we're after. But first things first, I mean, we already know that we have how to compute an unbiased estimate of a mean. How accurate is actually our estimate of a mean, right? If I give you 10 or 100 or 1,000,000 data points. That you can compute using the standard error. Standard error of your estimate, so mu hat is the average, or the estimated average. How do we compute this? Well, the standard error, that is basically just the variance or the square root of the variance of mu. And if you write this out, the square root of the square standard deviation of, and that divided by n. Just definition of variance. I mean, nothing spectacular. Now, that gives you numerically how certain are you that the value of mu that you got, the hat, right? I mean, that's how wide is the band in a way of where you should be looking for the true value. Now, if you just see that, suppose that I give you 1,000,000 data points, or I give you one data point, right? Let's go to these two of these extremes. And assume that somehow magically you arrive at the same squared here, right? Just by the division of n, either you divide by a large number or a very small number, the standard error will shrink really rapidly, right? That is the general idea. So more data, the better we can estimate things. Not just with means, but with all parameters that we have to estimate. So the more observations, the smaller the standard error. By the way, it's a very small interlude, also to the people on Zoom. These slides I prepared over the last few years, building on the slides that Thomas Lengauer, the director at the MPI for informatics, focusing on bioinformatics. I mean, basically, actually, the story of Thomas is also amazing. So he first studied mathematics and got his PhD, and like really top notch, like winning awards and stuff. And like, yeah, boring. Math. What is it useful for, right? I mean, that's so this was still in, well, not quite dinosaurs, but back in the Middle Ages. So computer science was still very new and novel. And he was like, yeah, I want to do something useful. And his dream was, in a way, to solve either cancer or that was not even not around, but stuff like HIV and stuff like that. Like, okay, math is not going to save the day, but it should. How can we make math save that day? Well, computer science. Computer science was a completely nascent new field. So he moved to the US, did his PhD at Cornell. Also, again, winning awards and stuff. So because now finally I know how to solve problems properly. And then he started applying it in bioinformatics in a third field, right? It's a special kind of crazy. And in all three fields, I mean, he won awards, and really, Thomas is amazing. He was also the one who kickstarted this course here originally. He retired a few years ago, and then, well, I sort of saved this course from never being taught again. So if in a few weeks/months you're like, oh my God, this should never have happened, I'm sorry. The blame is all mine, not Thomas's. Good. Some people may not. After one master thesis, I already had like, okay, this was really enough, right? And then I did do one PhD, but never again. To do 2 or 3, I mean, crazy. Good. Okay, that was an aside. I don't even know what inspired it. What are now the standard errors? Not of a mean, that's easy to compute, but of the coefficients that we have. So what is the standard error of beta naught, beta 1? Well, we can write it down relatively straightforwardly like this. I mean, I'm not going to show you exactly where it comes from, but the formulas that you saw previously, just by rewriting them a little bit, you can plug it, everything in, and there you are. So we have the squared sum of errors as the variance, and then this nice formula over here, which includes essentially your estimator. And as you see, the n, so the number of data points we have, and so that is a huge factor, and here it also plays a large role, right? I mean, so here we don't directly normalize by n, but yeah, if we have many points, then we have a high chance, of course, then even if we get things almost right, but not quite, the numerator will still be relatively large, right? That, numerator, denominator, right? I'm mixing it up. Anyway, the bottom one will still be large. So if we have many data points, the standard error will go down because we're able to estimate the beta naught much better, but only if, well, the variances between them are not so large, right? If our data just mean one big cloud, then we won't be able to estimate it very well, even if we have many points. Okay, so this allows us already to give some expression of how certain are we about the estimates of beta naught and beta 1 to be found, right? So we now know how to find these values, and we now know how to say something about how good or how bad are these. So let's go through a few next steps in assessing how good this is, and can we say something more about how confident are we about these values? So the standard error. Yeah, exactly. The first one, every time I read it, and really every time, and I've been teaching this course now for quite a few years, every time it screws me up. So even this morning when I was going over the slides again, like, what the hell? I mean, the standard error of beta 1 decreases if the xi are more spread out. Because if they're spread out, then it's very difficult to draw the line, right? Yes, but no. So it's more like what is meant here in the book is over here. If we have a widespread, and there's really like this band in your data, right? Then it's relatively easy to find exactly the line through it. Whereas if you have a more clump part of data, right, and that's that, right? So you just have a small clump, then yeah, well, any line between that will fit. If you of course have a small, I mean, a very nicely dense straight line, yeah, then it's easy again, right? Now, what is now the spread in the x? That's this one. So if it's nicely spread out, then it doesn't really matter if they follow it neatly. We just have a lot of data over a large domain. Every time this screws me over, and perhaps I should rewrite it, but then again, I don't want to deviate too much from the book. Beta naught, the standard error of it, if we have a, so if x is completely centered around 0, so we just plus and minus, then there's no big trend to the left to the right. Then, so that's if the estimate of, I should bring a mouse next time. That is easier for me. So if the average of x is around 0, well, that is great because then also the deviations, and we assume that the errors are also going to be 0-centered. So everything is around 0. We can almost wish it away, which means that essentially we can think away the whole linear, let's say the line, the slope, and then the intercept is just going to be the mean. Write it down as an example. I mean, think about it a little bit. I mean, that's it's relatively straightforward. Good. So, and that allows that both the estimate and the standard error are going to be the same. Now, the variance we don't know. Only if we have like the true data generating mechanism, we can compute this, because then we can ask, give me data or data generating mechanism, and do it again, do it again, do it again. And over each of those samples, we can then compute the variance. We only have one sample, so we're kind of screwed in that sense. However, we can estimate it. Again, building on the assumptions that I expressed a bit earlier, and I will express them again in the next slide. What we can have is the residual is it? Yeah, the residual standard error, RSE, is going to be the square root of the residual sum of squares, which you already know, divided by n minus 2. Minus 2 comes from 2 outer points that we ignore. Some statistical reasons mean that's just do minus 2 and you're good. Okay, so what do we now have? We now have a way, if I throw some data points at you, right, for x and y, you know, if you're willing to assume that, okay, there was a straight line generating this and there's some error around it, you know how to find your beta naught and beta 1, right? I mean, that, if I ask you, how confident are you about these results, right? These beta naught and beta 1, well, confident, I don't really know, but I can tell you what is the standard error. I mean, how, if you would give me more and more data of the same amount, same generating mechanism, I can tell you in what band I would expect those parameters to be, right? So we're already getting a bit closer to giving I think, a reliable answer. But the word confident has, well, a nice ring to it. Like if you're really truly confident, I mean, because it allows me to ask, like, well, how confident are you? And yeah, it lays within this band, not really, right? Also, from a statistics perspective, you have this notion of confidence intervals. I partially hope that you already know what a confidence interval is, and then it will just be a rehash. And if you don't know, then, well, this is going to be a crash course. Confidence intervals are, I think, one of the most beautiful inventions from statistics in the last, I don't know, 100 years, or perhaps they're even older. I forgot to look this up. What is the 95% confidence interval? That's the one that you read most about, right, in papers. That is the, so if there is so you have your estimate, right? Let's say of beta 1 or beta naught, right? I mean, your favorite coefficient that you just estimated. And now, and of course, if you're really lucky, this is the right one. Now, what is the interval? What is the range of possible values where you can give me some guarantees that the true value is in? Right? It's not the standard error, not like if you give me more and more data, it's roughly this band, but no, what is the interval in which you can give me a guarantee between quotes, the true value is in? Of course, if I give you one data point, this will be a super wide interval, right? Because only if you're super lucky that you would have gotten it, right? If I give you 500 million gazillion data points, this interval will naturally shrink, right? So that is definitely going to be part of it. Now, ideally, we would, of course, again, do the same thing. So I have the magical data generating mechanism, and I give you data, and again, and again, and again. Each and every time you compute your beta 1 and beta naught, and you can then ask me at the end, right, what was now the real value? And then we can actually compute what is now the interval, right? I mean, that's what is the closest interval between the estimates you had versus the one where the real value was. Now, we don't really need to go all that way. So first of all, we can define it like I have over here. This is the width of the interval. So this is for beta 1, and this is for beta naught. We have the estimated value minus twice the standard error for beta 1, which if we have this sigma, right, I mean, that's what we somehow magically will obtain. We can compute. The right-hand side, you can also compute. So this is essentially what are the values around your estimate, right? Twice the standard error. Apparently twice standard error has a magic meaning. And we can do the same thing for beta naught. Where does the twice now come from? Now, here we have a Gaussian, as you could have seen, right? Nicely colored. And here I have my mean. This is mu, right? That's where it's centered. Then if I now look at what area is colored within one standard deviation of the mean, right? So there's just a green area. This is 68.2% of the mass, of the probability mass. If I take twice sigma, then I have 95.4% of the probability mass. Okay, so that now corresponds one-to-one to what I have here. If I want to give you, if I want to ask from you, I want you to give me, what is the interval in which you're 95% confident that the true population interval lays? Well, then you're going to give me, around the estimates that you found, 2 sigma on both sides. That's the area in which you're 95% confident that the actual population value will lay. There's still a 5% probability of bad luck, but hey, such is life, right? I mean, you need to gamble a bit now and You can also see that, hey, if you say, okay, I'm not a gambler, right? I mean, there's cybersecurity people in the room, and not like, okay, I'm not a gambler, right? I want to be more certain, right? I mean, I'll accept that there's a tiny bit of bad luck possible, but let's keep it real. Then you could also ask, of course, for the 3 sigma. And then you have, as you can see here, that is just this entire range, right? That is 99.7%. Okay, well, that you can also do. Of course, you can even expand it further, but I mean, let's keep it real. Because before you know it, you will say, okay, well, I have this value, right? I have 1 million data points, and the average is 0.5, but it could have been 1 million or minus 1 million, who knows, right? That is not really useful. So 95% confidence interval, it's not just because people like 95, right? It sounds confident, it just comes from the 2 sigma, right? It's a happy coincidence with the Gaussian. Well, okay, where does this Gaussian now come from? And why is the Gaussian actually a good fit here, right? I mean, it's also a happy coincidence. We have assumed that our errors are 0 mean, right? So they're centered around the population line, and they're Gaussian distributed. And because we assumed that, our estimates of beta 1 and beta 0 also become Gaussian distributed. And that allows us to do this type of analysis. So is this now a happy coincidence, or was this by design? I was not in the room when they came up with this, but I think it was more out of mathematical convenience and like, oh, look how beautiful it all works, right? But it's a bit in line with if statisticians say that, okay, well, look at the real world, everything is Gaussian. Yeah, is this now because we know how to handle Gaussians really well, and we know how to mathematically write it, and that's why we see them everywhere, or is it the other way around? Don't know. Good. Let's see. We are now at slide 13. Let me very quickly give actually this example, and then we have a short break, and then we continue for a bit. So on the advertising data we saw earlier, right? We have the nice blue line again. We had beta 0, beta 1 already. What are the actual values? What are now the 95% confidence intervals? Building from the standard error, these are the following, right? So for beta 0, with 95% confidence, we can say that the true intercept lays somewhere between 6.1 and 7.9, and the true slope is 0.04, somewhere between 0.04 and 0.05. Okay, but that is nice because that means that with 95% confidence, we can say that, well, there's actually really something going on, right? Between, in this case, TV sales, TV ads and sales, right? It's not all of a sudden, for the latter one, that it really goes to 0, 0, 0, right? It's really between 0.04 and 0.05. It's not going to go much up, right? If you really expect magic, okay, wrong medium, but we're not completely wasting money either, most likely. Good. That's it for right now. Let's take a break of, let's say 10 minutes. 10 minutes, is this fair? Yeah, okay, I see somebody vigorously nodding. I also think it's fair. See you in 10 minutes again. So that was a nice refreshing break of 10 minutes of questions on answering questions. Good. Okay, let's get going again. We know how to estimate betas. We now know what the standard error of a beta estimate is, and we know what the confidence interval is. I mean, we already learned so much. By looking at this 0.04, 0.042, 0.045, 0.05, Jesus, it seems so small, right? Is it now significant? Is it worth reporting, right? I mean, there is something going on, but yeah. And of course, I mean, if the salespeople think that a value of 0.0001 is already amazing, then okay, that's their bet, right? But from a statistical perspective, we have learned these values now from data. Is it really worth reporting to them, or because 95% is only 95%? So what we want to do significance testing. Or in other words, we want to do hypothesis testing, right? The hypothesis being that, the one hypothesis that there's nothing going on in this data, and the alternative hypothesis that is going on in the data. And can we now say, with some statistical test, well, yes, there is really something going on, or, well, let's not get all riled up. So that's the setup that we have, right? We have H0, the null hypothesis, nothing going on, and an alternative hypothesis that something is going on. What does it mean in our case? In our case, nothing going on means a slope of 0, right? Completely flat. Doesn't matter what the value of x is, right? It doesn't give any information towards y. And the alternative, hence, is a non-zero beta 1. 0, of course, because of errors and limited sample size, are never really truly going to be 0. How large should it be away from 0? Now, the t-statistic gives us essentially a very nice tool to formalize this properly. So what we have is that we have here the beta 1, the one that we estimated, and then we look at how far away is it from our null hypothesis, right? So, and our null hypothesis in this case is 0, because nothing is going on. And we divide this by the standard error of beta 1. It's the t-statistic, also known as the z-scores, right? So basically we assume things to be Gaussian, we fit it to be a Gaussian, and then we interpret it as a Gaussian, right? You may have noticed that in the entire lecture I've been saying assuming a lot. That's what machine learning is really for a very large part about, right? We do not know how the world works. We need to make assumptions. What we will see, going ahead already to a few lectures later, there are plenty of methods that make much fewer assumptions, but they will need way more data. So a few examples of this, right? I mean, the flexibility and the overfitting that you get, we saw that last week. Our assumption here is everything is linear, everything is Gaussian. So just by looking at the z-score, this value of t, we can now get an inkling of an idea of how significant, how trustworthy in a certain way is our beta 1 away from 0. That's what we're doing here. Just looking at the values. So if beta 1, let's give it a value of, I don't know, 1, right? But if the standard error is now really small, right? Then, so really, really small. So we are really like certain, right, in 95% confidence terms, right? I mean, that is really, it's 1. Well, then the t value is going to be really high, right? And the other way around. So if the standard error is like, yeah, what could have been anything, then it's going to be very, very small. So the interpretation of this z-score and this t-statistic is really that large numbers, okay, there's something going on. Small numbers, okay, I mean, don't get all fired up. You can plot this for, you can basically analyze it for different sizes, population sizes. And what you see here, we plotted it here, but so the true normal distribution, and like I said, we're assuming normals everywhere. That is the green line over here. That is the bottom one. I should replot this and make this a little bit more visible. The bottom one is the green. That's the normal one. And the t-statistic approximates this roughly, but in a nice computable way, right? In that sense. It's basically, it's a hack. That's how you could say it. But you can also see is that the, what is it, ochre? The dark yellow line, it's a bit further away, and the blue line is a bit closer to the normal. Well, the ochre one is for 30 data points. Sample size n is 30. The other one is for 100. So you can see that, well, at 100, we're reasonably close to the green line. Okay, you can, it fits roughly to what the true Gaussian would be. And the fewer data points we have, well, it rapidly goes away. And common assumption or common, let's say, agreement is that 30 is sort of like, okay, well, then it starts to become critical. If you have fewer than 30 data points, I mean, friends do not let friends draw conclusions from fewer than 30 data points. So with more than 30 data points, we can then look at these t values, and then we can see, okay, is this worth anything? By now looking next, I had a break, but I didn't have the chance to drink anything. Given that this t distribution or t-statistic essentially follows a Gaussian, so that we have here, now it goes really close, that means that we can also consider these t values to be drawn from a Gaussian. Right? We see Gaussians everywhere because we choose to see them everywhere, but okay, it is again very useful. So if it is 0 mean, what is now the probability of getting a value that is far away from it? So at a t value of larger than 2, that follows here, it's roughly 5%. So t is again, why is this? A standard deviation, twice standard deviation, 95% confidence interval, right? So if we have a t value of t or larger, then we're actually 2 standard deviations away. Where could this value been drawn from? Well, just in this orange area or this orange area, because we don't really care about. And we look at a two-sided test right now. If we have a higher value for t, well, that means that it's drawn even further away from the tails. Well, by this Gaussian, this has a very low probability, right? There's almost no probability master anymore. So in the example that I had, right, so the difference was 1, but we had, the standard error was almost 0. So we had an enormous number, let's say 1 million. The probability of drawing a t of 1 million out of a zero-centered Gaussian, extremely low, right? So that means that under the assumption that the null hypothesis, that there's nothing going on in the data, okay, it is significant, right? I mean, that's by any means in that sense. Okay, now, writing this, saying this a little bit more formally, what we now have computed is what we call a p-value. And the smaller the p-value is, the more unlikely it is that we are observing a phenomenon that looks like a phenomenon, but actually was generated by the null hypothesis, right? So we assume the world to be noisy, so even if there's really truly nothing going on in the system, if we're just unlucky, we could get data that looks like this, right? It is possible. It's very unlikely, right? It should look like this, and maybe with a bit some spread, but we can get really weird stuff. That's what this p-value essentially expresses, right? That we draw the conclusion something is going on, where actually it was generated from a process that nothing was going on. P-values typically are considered at a cutoff of 5%, right? That's called the alpha, the significance threshold. So that means that in 5% of the cases that we say, okay, I think I have something real here. Okay, so 1 in 20 cases, actually we're looking at something bogus, right? And that's, this value of 5% or 0.05 comes from one of the first papers on this topic, written by Robert Fisher, I think in 1918, give or take, maybe 1921. And already then he said, okay, we'll proceed with caution. And this is just an example, right? 95% is convenient, but that's be careful. Long story short, right, fast forward to now, I mean, why are so many results in medicine and in social science, psychology particularly, I mean, not replicable, right? Why are so many great findings? I mean, like, yeah, wait a second, it actually turns out to be wrong. That's 5%, right? One in 20 cases is completely bogus. And if you now have 1,000 research projects, and all of them use a p-value and cutoff an alpha of 0.05, there's going to be quite a few false results, right? Spurious results. Good. So friends, do not let friends use 0.05 as an alpha, right? You need to be very careful in what you do. We'll revisit this 0.05 in a slightly different way, and the risks of it, particularly in one of the next slides. So this particular case, if t is larger than 2, we know the p-value is much lower than this 5%, and we're going to accept the alternative hypothesis. We reject the null hypothesis. And like I said, typical p-value is 5%, 1%, or whatever low number people are comfortable with. There is whole, I mean, I actually was planning to show a picture. I mean, I was dressed up as, I don't know, you could say a member of the Ministry of Magic in the day before yesterday. I was at a PhD defense in the Netherlands, a very formal affair, and I was like a big gown. I mean, maybe I'll if I get the picture, and I will upload it or include it in the slides next time. And one of the other jury members was Peter Grunwald, who is a very famous statistician and, well, sort of at the forefront in the fight against p-values, because in statistics land, people don't like p-values anymore. It's just that it became too popular and people are using it the wrong way. So hence he has quite a battle ahead of him. But I'm still teaching you p-values, so I'm not sure if he now likes me or not. But at least I tell you to be careful. Good. So what do we have here? We now have for the TV ads and sales, we have the coefficients. We already saw them earlier. We have the standard errors. We saw them earlier, and we can now compute what are the t-statistics, right? We just plug this in. We see that, okay, a p-statistic of 15 for the intercept and 17.7 for beta 1, right? For the TV sales directly. Those are very, very low p-values, right? So we could compute what is the probability of drawing a 17.67 or a higher value under a zero mean Gaussian with the appropriate variance. Very, very small. So yeah, there's really something going on, right? 0.04 7.5 may seem small, but there's definitely something going on. So let's see. If we now go to radio, what do we see? Well, a kind of similar picture, right? The intercept is still very significant, so there is some spending makes sense. The radio, so the slope is almost at 10, so also clearly very significant. Okay, good. Now let's look at newspaper. So the one where already last week I said, okay, I'm not sure, right, if I would put my money there. But intercept, okay, almost 20, great. 3.3. So that is still significant under this 5%, right? But it's probably, well, it's almost 3 standard. It's actually, this is the 99% significant in that sense. 9%. I still don't buy it. I mean, if I look at this line and look at this data, right, I mean, I'm like, I have this sneaking suspicion, and maybe we will find out today even, that it's not really the newspaper that is driving the sales, but that there's an interplay between radio and TV ads, and perhaps a bit of repetition in newspaper. But if I look at this, the orange dots there, I mean, I would advise against investing. Let's see if we can work through the math and get this conclusion. This is not one of those lies, damn lies statistics, right? An example of that. This is more like, okay, well, be careful, be careful. So, I'm going to throw at you 3 different other ways on how we can measure how good a model is. Just to make sure that you quickly have seen them. The residual standard error, we've seen it very quickly in passing. It's essentially how far in absolute terms are your predictions from the true value. That's essentially what it comes down. You can compute it directly using the RSS, which is convenient because now you only need to learn how to compute the RSS for reals, and then you could just translate it. We have the R-squared statistic. That is a very tricky one. Why is it tricky? It's both very useful and it's difficult to interpret. So it is the proportion of variance in the output that is explained by the input. So how much of the, let's say, if we assume Y to be just generated by noise, right? So it has a mean and there's some noise. How much of this noise can we explain away by exploiting structure in X? What type of structure? Linear dependencies, right? That's our only tool right now. That's the R-squared. Of course, if we can somehow fit now a line perfectly through the points, there's not going to be any error left, right? And as we can fit everything perfectly, R-squared is going to be super, super happy. How can we compute it? It's the total sum of squares minus the residual sum of squares divided by, easy peasy. Why do you need to be a little bit careful there with R-squared? You have this interpretation of variance, right? And with the residual sum of squares, that is kind of natural. I mean, not to really shrink it, but variance is one of those more. Okay, let me phrase it differently. If you really, truly believe your data is it's all Gaussians, right, all the way down, sure, R-squared. Otherwise, variance is a very tricky concept because where does it truly come from? Variance is a very Gaussian concept, right? That's why I'm a bit reluctant. Now, if we go from R-squared, then right around the corner is the Pearson correlation coefficient, or as most people outside of statistics know, it's been just correlation. It's one of the most stupid ways to measure dependencies, just linear, but it will suffice for now. We will use it throughout this course a number of times, and successfully so. If you look at this definition, it will be reminiscent of what we saw earlier for how we estimate actually the coefficients, right? This is very close to the estimating beta 1. We have here the deviation of X from its mean, we have the deviation of Y for its mean, and then the normalization here is slightly different. What is the correlation? The correlation is essentially a measure of how well can we fit a straight line on this data. Pearson correlation is happiest if there is a perfect line in the data and there is no variance around this line left, then you get a correlation of 1. There can also be an anti-correlation, so it goes from up down, that's a -1. And if it can't fit the line, maybe because there isn't one, or maybe because it didn't do its homework, then it will have a score of 0. right? And of course, a little bit in between. Good. What is written here at the bottom, so it does not extend to the multivariate case. Well, oh, sweet summer children of mine, please do believe this for now. Of course, right? I mean, we have not been just sitting still, right? And that we have all sorts of correlation measures for multivariates, but it goes a little bit too far for this course. So right now, this one, we cannot extend to more than 2 variables, which will, as we will see, be enough in many, many cases. Good. This would have been the perfect moment for the break, but hey, luck is not with us today. I mean, but at least the technical side seems to work reasonably so far, knock on wood. So why is this the perfect moment? Because now we're going to be moving from just regressing with just one x variable to including multiple x variables. So can we actually get to can we get some evidence from my intuition that we should not invest in newspapers? If we now want to include multiple variables, we need to change our assumptions, right? And we cannot assume anymore that there's just one thing generating everything, because that doesn't really make much sense. So what is now the new assumption? Well, the new en vogue assumption is the following, what we have here. Y is actually generated by a beta naught plus beta 1 times x1 plus beta 2 times x2, and so on and so forth. So we have P as the number of predictors, coefficients right now, and of course still the error term, right? This is how we believe the world works. We can rewrite it. I mean, we can rewrite it as this sum, easy peasy. I mean, that's for computer scientists, this will come natural. And we can also write it in linear algebra terms. So x times beta as matrices and vectors and stuff. I mean, that's personally not the biggest fan of it, but as we will see, it is super useful. So bear with me and bear with the rest of the world. A large part of machine learning is just linear algebra. If you don't want to do that, well then I still welcome you to the wonderful world of data mining, where you can shy away from it a little bit, but these days machine learning is a lot of linear algebra. So what do we have now in our case? I choose to believe that sales are generated somehow through some magical mechanism by some intercept or some basic sales, because people want our product anyway. Then the amount of advertising we do on TV, plus the amount of advertising on radio, plus for newspaper, and then a bit of noise. That is how the world works. And now I'm interested in finding what are now these values of beta 0, 1, 2, and 3. And what we've seen previously with this very simple plug-in formula, and that is not going to work that straightforwardly anymore, sadly. So before we can go there, I mean, what happens to the residual sum of squares? Well, that is relatively straightforward. In that right now, we still have our y hat out of our formula, and we have the actual value, so we still have squares, and we sum it. Okay, good. If we now write it out, y hat is not just a beta naught plus a beta 1, but actually it's this whole train of things. We can rewrite it, and there we have a nice linear algebra term again. Now, we can, similarly as we did before, for which we got this nice plug-in formula, we can still take a derivative, set it to 0, because it's still a convex problem. That is neat. That is neat. So what do we get if we differentiate? Did your homework for you, please. So I think this is also part of the assignments. If not, I mean, work through this, right? And that at the exam, I mean, I'm not going to give you, let's say, here's 100 data points and do everything, the complete derivation by hand yourself. But if there is a tiny small example that we doctored up such that it is doable by hand, well, there is a chance this may appear in the exam. I'm not giving you a guarantee, but I also don't guarantee it will not happen. Do practice, do practice. That's, perhaps last year this broke a few people's legs. Yes, hi. Then I go back to the last slide. Okay. Ah, yes, good question, good question. Yes, so where in the multivariate linear regression are the samples? Good point. I kind of skipped over this because it's a bit too natural for me. Here, y is a random variable, right? But, so in a way, you can see this as a nice compact way of saying, okay, this is y1 and y2 and y3 and y4 and so on and so forth, right? Same thing for the x's. So there we have x1, and then we have, in a way, in sort of this matrix kind of way. So here we had y1, right? Here we have x1, the first value of x1, second value of x1, and so on and so forth. So it's basically a nice collapse of this giant matrix, right? And so on and so forth. So here you see exactly where this happens, right? So the residual sum of squares is a sum over every data point we have, from data point 1 up till n. And for each, we look at, okay, well, what should the value have been, and what is then the value that we actually got by taking the first coefficient times the first value of x, and so on and so forth, ad infinitum. Yeah, clear? Good. Okay. No further hands, nobody wants to say hi. Good. Let's keep track of time. Yeah, so with the residual sum of squares that we had on the previous slide, we differentiate with regard to beta, because the betas are what we're interested in, of course. We obtain these things, and we're not done yet. We can't just push forward just like that. We need to make more assumptions, but just to make things mathematically neat. If we now assume that x has full rank, which means we have here at the bottom, and for all yeah, exactly. So that's so full column rank. Yeah. So there's essentially there's no way how we can reorganize things that one of the columns, one of the rows is completely useless, right? We really need every data point. That's how you can interpret it. There's no duplications of different attributes, right? So if I take x1 and then copy it into x2, it's exactly the same thing. My metric is not full rank because I can explain it one-to-one, right? So x2 is in that sense essentially useless. That's the intuition. So the idea is that if this would be the case in our data, we can catch it before it does any harm. We throw it out, and then we're good, right? So it's not the worst of assumptions. We set now in this case, multidimensional derivative to 0. We have this nice expression. We want to solve for beta, so we rewrite things. We arrive now, and after doing so, we arrive at it here. So we have the estimated. It's now a vector, right? Beta hat is now a vector. It's not one value of beta, it's a vector, right? It's basically beta 1, beta 2, beta 3, and all the estimates thereof. And this is essentially the data matrix, and this is what we would want. So what we would want it to spit out is the actual value. Now, let's skip the univariate case right now. We get the output, y hat. So the moment I have the value of beta hat, then this expression over here, this hand side, so the y is gone, this gives me an estimate of my y hat, right? So it gives me the estimate of y. So you can rewrite this back if you don't like the linear algebra. If I give you an estimated set of coefficients, and I give you the input variables, you can give me the output, right? The estimated output. It's not magic here. Now, rewriting it back into, so this is essentially what I said that we just did, right? So we have the input times the estimated coefficients, and then we're good. Rewriting this accordingly, we have here this blob, all these bold things, these x's, we call the hat matrix. So you will see this in the book, specifically in the ESL book, hence green plus. You will also see it in machine learning papers and whatnot. What's the hat matrix? Well, it's the matrix that puts the hat on y. Statisticians are so funny. Because here we have an actual y, and the hat matrix puts the hat on it because this expression gives us the estimated values of y, right? Good. In the assignments, this will be a useful tool. Now, suppose that we do this, right? Because essentially, if we now just do this, we get a vector beta of estimated values, estimated coefficients, and we're good to go, right? I mean, it's essentially as simple as we had previously for just the one variate case. It's just, it looks a bit more scary, but it is relatively straightforward. What are we actually doing? Because previously we were just fitting a line, right? And it was very nice to plot in 2D, and we could reason about the line and about the variance of the line and whatnot. I mean, what is actually going on now if we have multiple dimensions? To keep all our brains somewhat intact, I stick to 3D for now, right? But, so meaning I have x1, I have x2, and I have my output variable. So it's only 2D in the input, so to speak. What we're trying to find is not just the one line, but now we're trying to find that plane. So a 2D plane in this three-dimensional space, right? We always project down by one dimension. That explains as much of the variance as possible. So that hugs the points that we have, so all the red dots, as closely as possible, right? Creating as few of these strands again as we had previously. Residual sum of squares, so long lines incur a very large penalty, so we want to hug really, really tightly. Alternate interpretation. You could say that each of our input variables, they together create a p-dimensional space, right? In the example, we just have two. It's still relatively easy to imagine. So this x1 and x2, they're in some plane, right? Different directions. And we need the different directions, otherwise they would just collapse into one another, right? That's the assumption that we have about full rankness. So they're not the same. They point in different directions. What we're now trying to find is that. So we would like to predict this value, but we don't really know where it is. What we now want to do is find that direction and that point y hat within this plane that explains that is basically that is the projection of y onto this plane. So where y projects onto this plane, this is where we want to predict. And that we achieve exactly with what we've just been doing. I personally don't like this interpretation. This breaks my brain. The previous one, planes that hug points, this works for me. But and I see that most of you agree with me. Very good. I've also seen people agree with this, and well, I'm not sure if they're here. Good. Let me see. I'm gonna go a little bit forward, a little bit over time, 5 minutes or so, such that next time we then at least have the basics of multiple multivariate linear regression behind us. Yeah, so linear least square models are unbiased if the generating mechanism blah, 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 right? That's a Gauss-Markov theorem. Do look at it at home. Why? Where does this come from? So we have this expression, beta hat. This is basically how we find beta hat, right? That's so hat matrix times y, we have beta hat. What is now our definition of the model that we have? Well, that is y is essentially the data times this, the coefficient factor, right, plus some noise. As you can also see, even if I dislike this linear algebra in general, the notation is nice and compact, right? Just imagine if I would have needed all projectors at the same time. So what we're now going to do is I'm going to plug the definition of how we assume that the world works, this one, into what we actually do, right? I'm going to plug it in there, substituting line 2 into 1. So I now have this one here. I rewrite things a little bit because so I have this hat matrix thing times the first term plus the hat matrix thing times the second term. So first term over here, second there. And even if you don't like linear algebra, you will see that, hey, look, this is x transpose times x inverse times x transpose x. Let's get rid of it, right? That's just going to be 1. Okay, so this is what we now arrive at here. Now we're going to look at the expectation, because bias and unbiased is about, is it possible that if I give you infinite data, that you can get to the correct answer, right? Just think again about last week. If the true data generating mechanism is like a squiggly like this, and I allow you only to fit a linear line, then no matter how much data I give you, you will never be able to get a grip on the true model. You will always make some unnecessary error, right? If the true data generating mechanism is linear, then if I give you enough data, you will be able to get up to epsilon precision to the true generating mechanism, right? The latter case, you're unbiased. In the second case, it's basically the deck is stacked against you. It's a very unfair world. So in order to determine if something is unbiased or not, we need to look at what is the expectation, so in the limit, right, of a particular thing. In this case, beta hat. So is the beta hat given x, this is the training data we have, is this now unbiased or not? What are we going to get from our data? You could plug here in also for all I care y, because in the end that's also something that you train on, but just for notational convenience we didn't. So this is what we want to have, or this is what we have. We estimate beta hats, and we want them to be beta. This is what we want to be, right? So now this one, if we unroll it, how do we get it? Well, that's exactly this term over here. Okay, that is easy peasy. Now in expectations, I can break this up again, because which terms do I now have? Well, hey, I just have the beta, I break it up. This is just beta given x. Okay, that's one term. Then I have this one, so this hat matrix times the error given x, that is something else. These are completely independent. I mean, I can just break this up, because indeed input and errors are independent. I animate this very nicely. So now we have this term over here, and, oh, actually no, so for the next line, this expectation, this error, because it's independent and it's just, the expectation doesn't really matter anymore. But the next step, the final step, we get rid of this entire beast over here. Oh, wait a second, actually I said something nonsense. Okay, let me see. I have this one over here, up, and now I can push the expectation just to the error, because this term over here, the hat matrix, is just fixed on the data, doesn't have anything to do with the expectation, right? And that's, so just push it out. And then we have the expectation of the error here, and let's go back to our assumptions. What did we assume that in the true mechanism, what is the shape of the noise? It's zero mean. So no matter what the variance is, but if I give you enough data, it will be zero mean. So whatever the value of this hat matrix, right, times the expectation, so in the limit of the error, it's going to be zero, so the entire thing disappears. So this means I only have left the expectation of beta given x equals the expectation of b hat given x. Well, the expectation of beta given x in the limit is of course just going to be beta, because there's nothing to be estimated anymore. Hey, we have an unbiased estimator. So this means that, well, we're doing something sensible. Isn't that nice? Okay, my animation needs to be adjusted a little bit. I think that somehow the fonts are not correct on my slides here. So I will make sure that the slides that are uploaded are a bit more corrected, at least as far as I can check. This derivation was hopefully reasonably easy to follow, even though I made one little boo-boo, but I fixed myself. Where does this come from? This is the Gauss-Markov theorem. So we have it again, right? And I'm going to show it to you until you really read, all of you read it fully and understood it. That I can't check until the exam, but please do, please do. Okay, let me very quickly, yeah, so the next slide I can do and then we're done, I think. No, pretty much. So we have our three cases again. If we do a univariate regression, then, well, strictly by definition, we're just looking at one variate, x1, respectively x2, x3, and we're ignoring all the rest, right? We're just seeing how much can we explain y given x1, and so on and so forth. In multivariate regression, we have a slightly different interpretation, but I'll get to there in a second. So this is in terms of like, is it significant or not? Actually, that's what we should look at. So is it really adding information, yes or no, right? So if I want to know, does TV add information with regards to the rest? Well, what I do is that I essentially treat, so I learn the best parameters for the others, and then I'm going to see, okay, can I now find anything that to make it even betterer using, well, TV, radio, newspaper, right? That is the idea how we now test significance. So does it really add something new to the table? And if it doesn't, yeah, okay, then it's not significant, right? But just to get you wrap your head around it. So what we see is that if we now learn a multivariate model over these three variates, the intercept was not so interesting. It's significant. That's fantastic. Essentially, if we take out TV and we plug it back in, right? I mean, after learning the coefficients, 32 is a t statistic. So 32 standard deviations away from that is pretty damn significant. Radio, same thing. And newspaper, I mean, finally I got my money's worth, right? I mean, that's see, I knew it. Newspaper is not significant. It has, in this case, even a negative t statistic. Don't get too excited about that, right? The whole point is it's very close to 0 and it's below 2, right? And also, I mean, well, not, let's say, minus 10. I mean, that would be really interesting. Then something went wrong, I guess. What this shows is that newspaper, if can already be explained for a very large part, right, the effect of newspaper, by the other two. So maybe people who read the newspaper can also listen to radio, so there is some confounding going on. This is really going to be the last. Is it really? No. Almost the last. So it's about, again, so I already warned you about causation, right? Cause and effect. And I don't like, I love the word effect. I mean, we do a lot of work on causal inference these days, but in this lecture, I don't like the word effect. So what we see is that newspaper by itself was significant, but in this multivariate model, it's not. Where does this come from? Well, there's a very strong correlation. We saw how to compute it in a few slides before, between radio and newspaper. So it could well be that people who listen to radio also have newspaper, right? They're just like old-fashioned and stuff. And hence, if you spend more on newspaper, all this data was collected sort of in one big advertising campaign. Maybe we also invested at the same time in radio, and well, then it looks like the investment in newspaper paid off, but what does it mean? There was a confounding effect. We did not test every individual thing by itself, right? That is why causality is so ridiculously difficult. For example, number of storks is correlated, highly correlated with number of births. Why? Well, often storks live in relatively rural areas where typically birth rates are much higher than in highly densely populated areas. So yeah, I mean, storks cause babies or not, right? I mean, they're confounded. They're confounded. Number of gas stations correlated with number of divorces. So depending on where your preference lays, forbid the one or the other. I mean, or maybe it again has something to do with a third factor. This third factor is very, very often the case, right? Or a fourth factor, you know. If it's in the data, we call it a confounder. So if we have measured it, right? So if we have, in the first case, we have economic development in the data, then we have some glimmer of hope to find a model that actually, look, those places with a high or low population density, economic development, there we see high and low, this and this and this. So, okay, we don't draw bad conclusions, right? But only if we use the right model, which again, based on our assumptions, more often than not, the confounder is hidden. It means we don't have the data. It's somewhere, we could have measured it, or maybe we couldn't, I don't know. I mean, but we don't know about it, or we just simply don't have it. And hence you need to be really careful, like really super ultra mega careful to not draw causal conclusions. If you do not just linear regression, not just multiple linear regression, any type of learning from data, right? So you only have the data that you have, and that's that. Good, okay. Next week, we're going to be discussing 4 important questions, but that's for then. Thank you for your attention. Cheers.